Oops. Do 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 do. Do do do. Well, I got too many things. Oh, there it is. Haha, I found it. All right, so come on. You can do it. Uh-oh, did I ever move the camera? I guess I did. So we are currently in my chapter 4. Let us, I think this example 4 I'm doing is in my notes, so we can see the rest of it up here. So I do have, like, the first section is just a quick review of, power series if you're rusty on, like, what the basic formula is. I have a very quick synopsis of the most important things to know from Calculus 2. Like, ratio test is nothing we care about in here. All that time you spent, convergence, divergence, I don't care. For us, this is the convergence, divergence test, this over here. You draw a picture to find the singularities and think from there. That's it. So here, I used k instead of n, but it's the same thing. And after a bit, I derived what we just derived. Here's how it looks in my notes. Cj plus 2 minus 1 over j plus 2 times j plus 1. You know, it's the same pattern, but this one's got a j plus 2 and a j minus. I mean, I don't like that formula. I think it's better to rewrite it as I did and just cover it up with a screen. That's a better formula to work with. But if you sort through it, you see that, like, C4 is this, C5 is that, C6 is this, C7 is that, C8 is that. And so, you know, since C2 and C3 are 0, the C6 and the C7 are 0. On the other hand, C8 links to C4, which links to C0. So, like, basically, any multiple of 4 will always get linked to the C sub 0. Any multiple of 4 plus 1 will get linked to the C sub 1. Or in my notation on the board, A sub 0 and A sub 1. And so you just keep plugging it in and looking at it. And if you look at it long enough, you can find a pattern, which is this. There's a k factorial. You can factor out a 4 to the k, and that's what's left. You got a minus 1 to the k. It cycles back and forth, plus, minus, so that's why that's there. And if I study the 4k plus 1 terms for a bit, I can see a pattern there. It turns out it's minus 1 to the k over k factorial times 4 to the k times this. And so this is my general solution then. I've got the terms that I can factor C0 out from, and I've got the terms that I can factor C1 out from. But this would be my y1, and this would be my y2. These are the two fundamental solutions to this second order problem, which is still what we expect. Like, the theory you already learned is still relevant. Any questions? Now, could we solve this problem before? No. This is well outside our grasp. These are not cosine and sine. These are, you can call these whatever you want, all right? I mean, Spider-Man and, what do you guys want? Wonder Woman. So you don't think highly of this function, I guess, okay. I mean, all right. Wonder Woman. It's kind of disappointing. I don't know. Sorry, I digress. Okay, anyway, and if you were just looking for the first few terms in the solution, we would have found these, right? If I'd asked you to find the solution up to order 9, here it is, right? So if I ask a question like this on a test, and I do sometimes, I don't always assume that you can find the best possible form of the simplification of the form of the coefficient, right? You just kind of do your best, and I should be able to tell if you're, not wrong. So here's another example, but I'm going to skip ahead here at this point. So this is a definition you guys should know about. We say it's a singular point. There's a definition of, so I defined singularity over there in a somewhat vague way. There are particular kinds of singularities which are called regular singular points. Basically, it's a regular singular point if it's singular, but it's not too badly singular. In the following precise way, it's if it's a singular point, and yet if we multiply the p coefficient by x minus x naught and the q coefficient by x minus x naught squared, and these functions are analytic, which is to say that they have a convergent power series, right? So basically, if you can multiply the p coefficient by, an x minus x naught and the q coefficient by x minus x naught squared, and that removes all of the evil at x naught, then that's said to be a regular singular point. It turns out that there's a beautiful theory of how to solve differential equations with regular singular points. This method is called the Frobenius method. And here's how it goes. You've actually solved the Frobenius method already. So here's just some discussion about regular singular points. First of all, if you have a constant coefficient, there are no singular points. So the domain of those is everything. That's what we saw before. We solved the constant coefficient problem. Our solutions exist. In fact, they're analytic for the whole real line, because sine, cosine, exponential polynomials, these are all analytic. This one here, e to the x and cosine x, they're analytic, so this has no singular points as well, even though we couldn't solve it except now perhaps by our series methods if we had enough time. This one here, if I multiply x squared plus 1, the trouble with this, right, is if I put x equal to plus or minus I, that it zeroes out the coefficient of the y prime prime, and that basically means it's singular. So if you take this equation, divide by x squared plus 1, you notice that my definition, I assumed a y prime prime to judge the singularity, so I divided by the leading coefficient in order to make it look like this. And so if I do this, well then I've got x equals to plus or minus I as a singularity, but this is a regular singularity because if I multiply q of x by the x squared plus I or x minus I squared, I would get something that's analytic. All right, so enough about that. So this is the Frobenius theorem. Frobenius theorem says that a solution of y prime prime plus py prime plus y equal to 0, centered at an ordinary point x naught, can be extended to an open disk in the complex plane, which reaches the closest singularity. And, well, this is what I already told you. That was this theorem. A solution, on the other hand, of y prime prime plus py prime plus y equals 0 based at a regular singular point x naught extends to an open interval with x naught at one edge and x naught equals to plus or minus r on the other edge, where r is the distance to the nearest singularity besides x naught. So, you guys remember this problem? X squared y prime prime plus this right here. Remember that? Divide by x squared, what happens? Right? This has a singularity, right? 0 is a singularity for this. And in fact, it's a regular singular point, because if I multiply this by x squared, I just get c over a. And if I multiply this by x, I just get b over a. So 0 is a regular singular point for the Cauchy-Euler problem. So the Cauchy-Euler problem is actually the most simple, basic case of the Frobenius method. But this is why what's the domain for the Cauchy-Euler solutions? I don't know if you thought about this or not, but it's just like 0 to infinity. If we have x is positive, like that solution will make sense there. Or x could be negative and be like 0 to minus infinity. There is no other singularity for the Cauchy-Euler problem except for the origin, which is why the domain starts at the regular singular point and it goes as far as it can until it gets into the next singular point, which is never. So that's why the Cauchy-Euler problem has the domain 0 to infinity or 0 to minus infinity if you want to go the other way. But this method is, again, the same thing we already did, but there's a wrinkle. There's a wrinkle here. This is the theorem. Frobenius solution at a regular singular point. If we have a number A, if there is a number R, this is called the index of the problem. And there are coefficients A sub n such that y prime prime plus py prime plus qy equal to 0 has a solution. Well, it has a solution of this form. We can pick coefficients, constants, A sub n, times x to the n plus r. Now you might say at first glance, as I did when I was studying these things to start with, well, how is that different? Isn't this just a power series solution, right? But here's the rub. R solves what's called the indicial equation. The indicial equation is just a quadratic equation defined by R. This R can literally be anything that's a solution to a quadratic equation. It could be a complex. Little r could be a half. It could be a third. It could be minus a third. It could be all kinds of stuff. And as such, that's not a power series. It's something else, which is why it doesn't have the same domain structure as like power series. So the indicial equation ends up being this. And here, I'll just show you one. So like, here's how you solve it. If I'm going to solve this Frobenius problem, 3x y prime prime plus y prime minus y equals 0, what I do is I take the Frobenius solution, which is this, and first of all, I'm re-indexing it so I can add it together nicely later. So I take, this is my general solution. I differentiate it. How do you differentiate this? Well, check it out. N plus r times x to the n plus r minus 1, just power rule term by term, just what we did before. Y prime prime, same thing, but now we multiply by, n plus r minus 1, like that. And so there's my 3x y prime prime. Then all you do, take those, put it back in the differential equation, and this happens. There's some terms that are special cases, just like in the calculation I did for you today. These special terms are only going to go to 0 if we choose a specific value of r. That's the indicial equation. So this one, my indicial equation is this, and this is the analog of my red boxed equation today, but this time for the Frobenius method. And then you solve these recurrence relations. And this one happens to have an index of either 2/3 or 0. And so it's pretty much the same method I just showed you for the last example in class. It's just now we have to deal with this r floating around, and we get these solutions, which are, well, they're a bit exotic, I suppose. Listen, so this method, the Frobenius method, is a deep and important method for mathematical physics. The solutions for most important equations of math physics are derived in this way, like the solutions to the hydrogen atom in terms of special functions. Pretty much all special functions are derived from the Frobenius method. And so in some sense, that's beyond this course. So I don't test this that deeply. To whom much is given, much is required. I'm not giving you much on the Frobenius method. In fact, I think given the sparse amount of class time I've spent on it, I will not even ask you a homework question about the Frobenius method, if that's okay with you guys. Nod yes, emphatically yes, all right. Because you don't want to do this, right? Because when it's complex, when there's a repeated root, funky stuff happens. Like, it's a really interesting method, but I feel like it belongs in the second differential equations course, honestly. Although this will soon be the second differential equations course if everything goes as it's supposed to. Anyway, so you can read this. If you'd like to talk to me about the Frobenius method, I can tell you more. But I think I'm just going to test you guys on the series problem and also the domain theorem, of course. And I haven't written your next homework yet, but I will soon. And I need to give you back your test. So let me stop here for today. So there were some people who did well, and there were other people who did not do as well.